Britain's iconic bridges, spanning our most dramatic landscapes, have not only linked our island, but made it great.
These are the bridges that are known around the world, built by visionaries like Stevenson and Brunel, who are famous even today. Look at this!
From the banks of the Tyne to the mighty Thames, from the Firth of Forth to the Menai Strait, I'm on a journey to discover how those great bridges were built.
Here we go.
And the sweat and sacrifice that went into their construction.
Stopping traffic.
I'll uncover the huge egos, flawed geniuses and jealous rivalries behind their creation.
It's as if he'd been airbrushed from the whole story.
These are Britain's greatest bridges. On the eastern fringes of the British Isles, there's an extraordinary structure that is somewhat forgotten. It's a record-breaking structure that changed engineering forever. And we've been given special permission to explore it, from bottom to top.
Oh, wow. Oh, my goodness. This is something special. It's so high up. It's nothing apart from these two cables which disappear off.
This is the Humber Bridge. Its length from end to end is more than 2 kilometers. And between the two gigantic towers stretches one of the greatest engineering feats in history. The suspended central span is 1,410 meters long, and when it opened in 1981, it was the biggest suspension bridge on the planet.
Just look at these two enormous cables. They're about 70 centimeters thick. Each of them weighs over 5,000 tons. And then there's the towers. The one I'm stood on here, on the north side, and the one way off in the distance. Now these things are so tall, they're actually further apart at the top than they are at the bottom. And you know why? Because of the curvature of the Earth. That's the scale we're talking about here. The whole thing is epic.
For nearly 2 decades, this colossal edifice reigned supreme, the longest span of any suspension bridge in the world.
For many, including me, the Humber Bridge is one of the most beautiful bridges ever built. There's an understated simplicity that I just love. The way it disguises thousands of tons of concrete and steel, like a feather floating effortlessly across the water.
But building this record-breaking bridge was far from effortless. It was a severe technical challenge. Extraordinary political power struggle.
So just what did it take to build the longest bridge in the world right here in Britain?
As with most great bridges, the story of this one begins with a stretch of water that many people thought unbridgeable. The wide Humber estuary. Formed by the combination of 2 great rivers, the Ouse and the Trent, and almost 60 kilometers long, this tidal inlet divides a major industrial region in half.
Let's have a little look at the lie of the land. So I've come up the North Tower. So this is the north side of the estuary. Off in the distance there, the city of Kingston upon Hull. This is Yorkshire. Across the other side, away over the expanse of the bridge, it's the south side of the estuary. That's North Lincolnshire. And if you look out east, you've got the town of Grimsby, and further east, you're into the North Sea.
Before the bridge was built, driving from one side of the Humber to the other involved a 70-mile road journey that could take 2 hours or more. The only way to cross quicker was to ride on Britain's answer to a Mississippi paddle steamer. The paddles on the steamer allowed them to navigate very shallow waters. But the silty Humber was so shallow in places, the ferries still ran aground from time to time, stranded in the middle of the estuary until the tide changed.
Amazingly, decades since it was put out of a job on the Humber when the bridge opened, you can still hop aboard one of the paddle ferries today, here on the banks of the River Thames in London.
Now permanently moored and used as a popular bar, the Tattershall Castle, as this vessel is known, is in remarkable condition. Stepping aboard is like walking into a long-forgotten world.
Now this is the engine room. It was built in the 1930s. If you look, you can see all these beautiful brass fittings, this great big crankshaft and connecting rods. And down here, you can see where the spindles would be attached, and there'll be another one on the other side, and they'd head straight out to drive the great big paddles on each side, on the outside of the hull.
Sadly, the paddles have long since been removed, but you can see the deck extensions that once sat above them. These images show the steamer in its final days, under the ownership of British Rail. The Tattershall Castle put in 39 years' service on the Humber before being brought to London in 1975. But the fact that this old paddle steamer should end up here on the River Thames is oddly fitting.
You see, it was right there in the Houses of Parliament behind me that this ferry lost its job on the Humber. It was a casualty of a fierce political struggle that saw the voters of Hull being offered what was seen as an extraordinary election bribe, a bridge. A bridge that was set to be the longest in the world. When the Humber Bridge opened in 1981, it was the longest single-span suspension bridge ever built, with a road deck 2.2 kilometres long.
This new roadway connected communities on opposite banks of the estuary that used to be 70 miles apart by road. Overnight, they became brand new neighbours. But more than that, this record-breaking bridge formed the promise of a new future for this part of Britain. It would spur the creation of a new industrial hub for the nation.
But it wasn't quite for such public-spirited reasons that the bridge really got built. It's widely held that it was in fact the result of some rather more calculated political game-playing.
Back in the 1960s, the folk of the Humber towns had already spent decades campaigning for a new bridge. Theirs was the only estuary in Britain that didn't have one. But a bridge that could span this expanse of water would not only have to be extremely long, but also very tall. There are 4 major ports on the Humber that carry a hefty 13% of the UK's seaborne trade between them.
With 4,500-ton cargo ships regularly passing the bridge, the deck had to be high enough to allow them to float underneath. But the design also had to take into account what goes on under the water.
The Humber estuary has a very soft bed, with deep channels and shallow banks that can shift over time.
As those deep channels move, the shipping lanes need to move with them.
Most kinds of bridge able to span a river this size require a whole series of supports, leaving only narrow gaps for shipping that could easily silt up. But there's one type of design that needs just 2 towers. A suspension bridge could cross the water in one giant leap, allowing ships to follow the channels as they change.
So, to keep the full width of the estuary open, this bridge had to be a suspension bridge. And with the banks more than 2 kilometres apart, it would be the longest single span ever.
Despite their advantages, suspension bridges are complicated and therefore costly to build. No one seemed willing to spend the kind of money needed.
Then, something happened that would make the expense of such a construction all of a sudden worth it.
to the government. This man died. Henry Solomons MP. Harold Wilson's Labour government was made highly vulnerable by the death of Mr. Solomons. A by-election for his Hull North seat was set for the 27th of January 1966. If Labour lost, Wilson would be left with a majority of just one MP. For Labour, a win was crucial. Wilson dispatched his most experienced political operators to win over the voters, including the Transport Minister, Barbara Castle. Mrs. Castle stood up to give a speech to 200 people crammed into a local school hall. Everyone expected some kind of road improvement carrot to be dangled, but then she came out with 6 words that nobody anticipated. You will have your Humber Bridge. 9 days later, the people of Hull went to the polls, and here at the City Hall, the votes were counted.
Joseph Kevin McNamara, Labour, 24,000.
It was a victory for Labour. The bridge would finally be built. But 6 years later, when Wilson was voted out of office, there was still no bridge. Surprisingly, the man who defeated him, Conservative Prime Minister Ted Heath, revived the scheme. Heath had plans for a new industrial county called Humberside. It would take in the whole estuary, from Hull to Grimsby and beyond, with the new bridge at its heart. Leading the project would be the firm of Freeman Fox and Partners, run by Sir Ralph Freeman. Freeman was the world's best suspension bridge engineer. His other hits include the Severn Bridge and the Forth Road Bridge. If Sir Ralph could make this ambitious design a reality, it would be the pinnacle of his career. Ground was finally broken in July 1972. If you stand here and look out over what was the biggest suspension bridge in the world, you might have a job puzzling out just where they started building it. I mean, how do you get 2 enormous cables weighing 5,000 tons, 155 meters up in the air, with a 2-kilometer-long road hanging off it? The answer is to start where every suspension bridge must, with 2 enormous holes in the ground. These holes will form the foundations for the towers. The towers will then be used to hold up the suspension cables. And from those cables, the road deck will be suspended from a series of smaller vertical cables called hangers. But it all starts with the holes, and digging those is not as easy as it seems. If you've ever dug a hole on the beach before, you know it doesn't take long before it starts filling up with water. And what I've created here is much more of a murky pond than any kind of basis for a 155-meter suspension bridge tower. The way to make a dry hole on a wet beach is to use sheet piles. These long interlocking strips of steel are literally hammered into the ground to create a curtain of metal. On the Dutch River, one of the Humber's tributaries, Phil Boys of the Environment Agency is driving piles into the riverbed as a flood defence. As one sheet goes down right next to the other, they kind of join, do they? There's a bit of a joint between them.
There is, yeah. On the edge of each pile, there's what's called a clutch. So one is, it's a curve of steel one way, and then it's curved the opposite way on the next pile. So that helps the 2 piles interlock, and then the vibrating hammer essentially just vibrates the pile at a very high frequency, and that's what helps drive that pile down into the ground.
Essentially, it's using brute force to get this sheet down into the ground. That's very clever. Now I understand the idea behind pile driving. Phil is letting me put the theory into practice. So by doing that, we're going to just build up the pressure in the hydraulics.
Yes, that's the one.
Here we go. Away it goes. And down it goes. I mean, look at it. what is here just a small flick of a switch triggers an enormous amount of power over there. This is high-tech equipment doing its job. It's powerful, it's unforgiving, it's blooming loud. It's the Gordon Ramsay of the construction industry. Here we go, look, that's it, that's the signal. Just giving it a quick check there to make sure it is nice and level. Everyone's happy. Job well done.
At the Humber Bridge construction site, hundreds of tons of sheet piles were driven deep into the riverbed, forming a dam of steel around the location of each tower. That allowed diggers to excavate the area inside the dam without fear of the walls caving in or the hole filling with water. Once the hole was deep enough, the next major step could take place, filling it in again, because a strong foundation made of solid concrete was needed to support the first of the two towers.
A year and a half into the project, they'd now cast a huge slab of concrete into the hole, 44 metres long, 16 metres wide, and 11 metres deep. It's still there, hidden away under the beach. And so the time had come to begin the first really revolutionary feature of the bridge. A 155-metre tall tower, to be made for the first time anywhere on a long-span suspension bridge, out of concrete.
Concrete is magic stuff. When it's first mixed, it can be poured or moulded into almost any shape, and when it sets, it's as tough as stone. The Romans were the first large-scale users of concrete. They used it on the world-famous Pantheon in Rome. Its dome is one of the biggest in the world made of concrete, and it's been standing for nearly 2,000 years. But suspension bridge towers are subject to quite different and far greater forces than most buildings.
The thing was, up until that point, suspension bridge towers had almost always been made out of steel. So the bridge designers had to be absolutely certain that a huge concrete tower would be equivalent in strength. And the reason they could be was all to do with these oranges.
The Humber Bridge is still standing today thanks to a French gardener called Joseph Monnier.
It was the 1860s, and Monnier worked at the historic Royal Palace in Paris, where one of his jobs was to look after the exotic citrus plants. Every summer, he'd have to move them from inside their glasshouse to the gardens outside, but the concrete pots they were in kept breaking.
The problem is that whilst concrete is very strong under the force of compression, it's very weak under the force of tension. So any sideways pull, like when a heavy lorry crosses a suspension bridge, could cause it to crack apart. Monnier found this same problem when he tried to drag his orange pots around the garden, until he made a simple change to their design.
Monnier discovered that if he put iron rods into the concrete as it set, when it hardened, it was much stronger.
That simple addition, adding metal rods to create reinforced concrete, totally changed its behavior. This new form of concrete is as strong in tension as it is in compression, making it perfect for almost any kind of structure. By the middle of the 20th century, architects and engineers were finding amazing new ways to exploit its properties. The engineers at Freeman Fox wanted to take that one step further. They knew using reinforced concrete instead of steel could save months of construction time and millions of pounds, if they could find a way to get it into place quickly and safely. Because even if the concrete itself was up to the job, most methods of casting it weren't.
A typical way to make a concrete structure was to precast it into small pieces and hoist each one into position by crane, one by one. But that was out of the question with the kind of heights they were talking about here. Hey! Another option was to cast the entire structure in situ. But you can't build a 155-metre high mould and pour concrete in from the top.
So that's when they turned to another fashionable new building technique. It was called slip forming, and it had proved successful in building a futuristic hotel and casino in Las Vegas. But could Freeman Fox transplant this technology from the parched Nevada desert to the watery world of the Humber? It was a gamble they just had to take. The Humber Suspension Bridge, with its world record-breaking span across the Humber estuary. It's a triumph of 1970s engineering. It used new materials and groundbreaking methods and remained the longest unsupported roadway until 1998. One of the challenges facing the bridge's designers at Freeman Fox was the massive towers that such a structure needed. They would be some of the tallest ever built from concrete, but most existing methods for pouring the concrete just weren't suitable. So they took a punt on a novel technique. The technique enabled tall structures to be built quicker and more efficiently than ever before. It was called slip forming. Slip forming gained popularity in the 1960s after being used to build a 31-story tower in Las Vegas called the Landmark. Building a giant 155-meter-high mold, then pouring concrete from the very top, would be technically challenging, really costly, and take far too long. But slip forming needs only a small mold, about 6 meters high. As the lower parts of the new tower dry and harden, the mold is shifted or slipped up a few centimeters on jacks. All the while, the concrete is poured without interruption. The mold moves continuously upwards, leaving behind a single solid structure. The technique worked impressively. The Humber Bridge towers proved that slip forming is quicker, cheaper, and safer than just about any other method of concrete construction. In the years since, it's become standard practice around the world for almost any kind of tower.
If you look here on one of the Humber towers, you can see a series of horizontal lines where the concrete was poured a few inches at a time. It's almost like it's got a grain to it. Working constantly, it took just under 6 months to reach the full height. That's an average of 7.6 centimeters an hour.
I'm meeting John Bailey, a local man who had a bird's eye view of this building revolution.
John, you worked on top of the towers. What was it like up there?
Initially, it was a little bit scary because you were going into the unknown. You'd never been up to that height before. When you get up to over 500 foot, then things look a little small from the top. So it was, yeah, your heart was in your mouth most of the time.
And so as the towers grew, the kind of all the infrastructure here,
everything was there.
With it.
Yeah, you even had well, you can see there, this is the canteen. This is where the guys would have their lunch or whatever, you know, if it rained.
So what were the conditions like working on the bridge? I mean, you were up there in all weathers, I guess.
If the weather was bad, you didn't go up. It was brutal up there, especially with the wind chill factor. You could get down to -20, -30 up there.
Jeez.
And it was cold. Some of the things the guys used to wear, I know one guy used to pinch his wife's tights because it's keeping him warm in the winter. It was a standing joke. The idea was if you climbed the tower, it was 45 minutes and 3 cigarettes.
To get from bottom to top.
The North Tower was finished in May 1974. Next, they needed to repeat the slip-forming process and build the South Tower, this time in the river itself. But when engineers prepared to start work on the foundations, they discovered a serious problem with the sheet piles surrounding the site.
The design called for this man-made island for the South Tower to sit on. But unexpectedly strong tidal currents ruined the sheet piles they put in to build it, helping cause a crippling 2-year delay.
Work on the rest of the bridge relied on both towers being up. But the sheet piles had to be reset and the foundations dried out. Project bosses were desperate to claw back some time.
Amazingly, with the experience they gained on the first tower and by working round the clock, they had this second tower topped out in nearly half the time, increasing their average climb rate to almost 11 centimetres per hour.
Building the entire bridge was supposed to take just 5 years. But by 1976, 4 years into the project, only the towers were complete. The next major task was to lift the suspension cables up to the top of the towers. But unless they were securely fastened at each end, they would quickly come straight back down again. I'm descending into a tomb-like structure at the bridge's southern end called an anchorage. It's really nothing more than a 200,000-ton slab of, well, you guessed it, concrete. The titanic weight of this structure and its partner on the opposite bank is all that stops the two cables from crashing into the river. But buried deep inside the anchorage is something totally unexpected.
Wow. I mean, you know you're coming deep down because of all the ladders that just keep going, but I don't think anything prepares you for this. Just listen to that echo. More.
In here, it's apparent that the suspension cables are not two enormous wires, but actually thousands upon thousands of small wires, each just 5 millimeters thick.
What you can see right above me here is where one of those main cables that runs the entire length of the bridge comes in to the anchorage. And where it comes in, what was that great big fat cable splays out into 37 different bunches of wires. And then these rows of orange blocks behind me is where each of those bunches are anchor pointed deep down into the concrete. And anyone who ever said engineering was dull and ugly has obviously never seen this. It's absolutely beautiful.
The 404 wires in each bunch are hooked onto giant bolts, each sunk 20 meters deep into the concrete wall.
Each of these loops was carried across the Humber individually. There are nearly 15,000 lengths of wire in total. If you were to drive across the bridge in a small car, each of these wires would carry just about 30 grams of it.
All modern suspension bridge cables are made this way for two reasons. Firstly, if one of these wires should snap, there are still 14,947 remaining to hold the bridge up. The other reason is that dragging a 70 centimeter thick, 5,000-ton cable to the top of one tower, across a 1.4 kilometer gap to the other tower, then down the far side, would be impossible. So how is it actually done? To find out, I'm meeting with Bill Harvey, one of the engineers that worked on the job.
Getting those cables up is just amazing.
I mean, we're right under one of the main cables here.
Yeah.
What you can't see from here is actually what's inside this sheet.
There's lots and lots of pieces like that.
Pieces just like that. It's incredible, isn't it? I mean, to think that is what's holding up, well, us right now, this whole roadway, all the cars, all the trucks that keep thundering past. That's marvellous. So the process of actually getting cables all the way across,
It's called spinning because they use a wheel, and the wheel is actually just a pulley.
The curious method of spinning was invented in the 1840s by American engineer John Roebling and used on almost every major suspension bridge since. It involves a pulley system that draws the wires across the span, pulling them off a huge drum at one end. Bill and I are going to recreate the principle on a smaller scale using string.
If you imagine a 5-ton reel of wire fastened into the anchorage.
So this is me over
here,
on, let's say, the north.
Over on the north bank. And then a spinning wheel pulling it.
So I run this right across the
river,
across the estuary.
And you'll see how fast this is unreeling.
Okay, yeah.
And then it gets looped there. And those bits get adjusted.
Yeah.
And then another loop is taken.
So actually, in that one journey across, I brought over 2 strands of wire.
And actually, there are 2 wires on the spinning wheel as well, so you've taken 4, and then you take another 4.
Wow, so this speeds things up hugely.
Yeah. And then, when you've done that 101 times, and there's 404 wires, you've got what's called a strand, and there are 37 strands up there.
How long would that?
It's going to take about 15 minutes to do a trip, times thousands and thousands of times.
To build up this great big cable that we've got here now.
Yeah. And the guys who are working here just have to stand here and maybe stand in the middle of the river on the catwalk and catch the wires as they go past and anchor them.
So you'd have guys dotted along?
All the way along.
Just to kind of make sure and guide it and make sure everything's going correct?
Yeah.
And they'd be just stood up there, what, all day long?
All day long. Standing on that.
Even though 4 wires could be spun in just 15 minutes, it took 22 months to finish this part of the job. In October 1979, the last and most complicated major process could finally begin, erecting the 21,000-ton roadway, the deck. This, of course, is what it's all about. Everything else, the towers, the cables, and the anchorages, all exist just to carry this ribbon of highway across the water. You might think that once the deck was in place, the whole suspension bridge would be solid as a rock. But that's where you'd be wrong.
To see how much the bridge moves, even on a relatively calm day like today, just watch this coin. I've popped it down there, right up against the edge of this expansion joint, which connects the main bridge deck behind me and the side span there. And look at it go. You can see it's moving. That's a good 2 or 3 centimetres there already. And it's the bridge deck where I am on this side that's moving. It's the gentle flex and sway of the bridge in the wind and with heavy traffic. It's almost like it's breathing in and out.
As cars and trucks thunder over the bridge, they cause the deck to jiggle a bit. But the bridge has to cope with a far greater force than traffic, the wind. And when the wind picks up, movement in the structure is essential.
Imagine a tree and a brick wall in a gale force wind. A tree bends and flexes. It's much more likely to remain standing. The brick wall acts like a huge sail, takes the full force of the wind and blows down much more easily. Likewise with a suspension bridge, a bit of flex and sway is a good thing.
But if you get your sums wrong, a bit of sway can turn into something much more extreme, and the whole bridge could come crashing down.
As slender and as elegant as it may seem from afar, it's not until you get right up under the bridge deck like I am here now that you get a true sense of the size and the strength of this thing. It's actually quite intimidating, like some kind of ridiculous spaceship slowly drifting overhead.
Lifting the 17,000-ton steel road deck into position in 1979 and keeping it there forever was going to be a serious challenge. That's because suspension bridges have an invisible enemy, the wind. To resist the force of gales, all of them are designed to allow sway. But one chilling lesson from history illustrates how this necessary flexibility can go badly wrong. In 1940, a suspension bridge across the Tacoma Narrows just outside the US city of Seattle began to swing in a way no one intended. Even before the bridge was finished, it would buck like a bronco in high winds. Construction workers nicknamed her Galloping Gertie. Eventually, this curious ripple turned into a full-blown wave, and just 4 months after it opened, the entire bridge ripped itself apart.
There was something about the design of the roadway on the Tacoma Narrows Bridge that magnified the way it behaved in the wind. Something the designers on this bridge had to completely avoid. And the best way to see how they did it is by going down in here. I'm going inside the bridge deck. So you leave the daylight behind, coming right down into this huge cavernous void. And it's noisy too, with the cars and trucks going overhead. And they're literally right overhead, just there. So this is the middle of the bridge deck. It's the series of these vast, hollow steel boxes, which continue for 1 kilometre in that direction, along to the north side of the river. And then another kilometre all the way down, back in that direction too, over to the south bank. It's really odd down here.
Each one of these boxes was prefabricated on land, but getting them into place was no easy feat. Starting at the dead centre of the bridge, they were floated into position, then hoisted one by one with huge cranes, which themselves hung off the suspension cables. Each box was then welded to its neighbours to form a continuous deck. And it's the shape of that deck which ensures the Humber Bridge will never gallop like Gertie.
Along the entire length of the bridge deck, it's flat here in the centre, above and below me, and then it slopes away at the sides. You can see it much better on this model here. So underneath, it's shaped like a saucer, and over the top, it's shaped, well, like an upside-down saucer. Compare that then to this model here of the bridge deck on the ill-fated Tacoma Narrows Bridge. You can see they're very different. This one is much squarer, and it's got these solid side barriers all the way along. So let's see what happens to this with a little bit of wind. Now you might expect the bridge deck just to be pushed away by the fan and kind of stay there until I turn it off. But give it a sec.
It starts to sway gradually, but it doesn't take long for the Tacoma model to waggle erratically.
But look at that. It's going absolutely berserk. It's oscillating back and forth. It's a phenomenon called flutter.
At Tacoma, a strong wind pushed the bridge to one side, lifting it slightly. But gravity and tension in the cables pulled it back down, and rather like a playground swing, up the other way. The wind then amplified this movement, pushing it further in the same direction. Then gravity and tension pulled it back even harder. The back and forth motion got stronger and higher with each swing, until the bridge failed.
Change the design of the bridge deck. Watch this. It's the same fan, it's the same springs. Let's see what happens.
This model is much more streamlined in shape, allowing the air to flow over it far more smoothly.
Not much so far.
But it does something else that's remarkably clever.
It's the difference in lengths between the lower and upper deck that has the strange effect of lowering the air pressure under here compared to on top. Now effectively, that forces the bridge deck downwards, pulling on the suspension cables. The bridge is bracing itself into the wind, and the windier it gets, the more stable the bridge becomes.
But during the complex process of assembling the deck, it was anything but stable. And in March 1980, disaster struck. At the north end of the bridge, one of the 40-ton cranes broke loose and tumbled 70 meters down onto the incomplete roadway. the joints ripped apart, leaving 2 boxes dangling precariously.
The Hull Daily Mail reported the dramatic accident, which happened just up here behind me, saying a man was hanging on for his life and that the sections were swinging like seesaws, hitting each other with a sound like a clap of thunder. It was a miracle nobody was killed, and amazingly, the damage done was minimal. But the whole incident was a very close call.
What could have been a catastrophic disaster only set the timescale back by a few months. In December 1980, the final box was lifted into place, completing the span. The mighty Humber was bridged at last, but it came at quite a cost. £151 million in total. What's more, it had taken 9 years instead of 5, and thanks to the rocketing inflation of the 70s, it was 81 million over budget.
Some people criticised the bridge as a white elephant, a bridge from nowhere to nowhere that should never really have been built.
Despite all that, this structure was celebrated as a national achievement, the latest in a long line of groundbreaking British engineering landmarks. And no less a person than Her Majesty the Queen opened the bridge on the 17th of July, 1981. I'm meeting Rachel Stainforth, who was there that day, aged just 6.
So the Humber Bridge has been here ever since you can remember, Rachel?
It has. It's been a huge instrumental part of our family. At the time, my granddad was chairman of the Humber Bridge Board, and my nan was Lord Mayor of Hull. So, because I was in the family, I got asked to give the official bouquet to the Queen on the opening of the Humber Bridge. So I was 6 at the time, I think.
And on the day, did it all go well?
I did have a bit of stage fright at the beginning, so I had to have a nudge and said, you know, get on with it, sort of thing. And so I did that, and she was very pleasant. I think I looked at my granddad the whole time and not her. But yeah, it was a really good day. I think now, you know, as years have gone by, that it's very much a focal point of the city and in the people of Hull's their hearts.
Her Majesty made the first official crossing. Behind her, eager motorists queued up for their first turn. The toll charge? £1.
Did you get a free toll pass?
No. No, afraid not. Even my granddad didn't, although he was the first person, he was the first toll-paying car to go over.
Okay, very good.
Yeah.
Very good. The Humber Bridge is perhaps a bit forgotten about, slightly off the beaten track of Britain's motorway network. But we should remember that here in the UK, we have a world record-breaking structure. What was, for 17 years, the longest single-span suspension bridge on the planet. And it is a bridge to be proud of and to boast about, because we made it, and we made it here.